Howdy folks, Mr. Reed here, and welcome to One More Question. So what I'm going to be taking a look at today is the idea that there is an inverse to exponential functions. We're going to kind of, stumble our way into it, just kind of exploring it slowly, and then we're going to give it some notation that is widely accepted after we've kind of seen how it would look. So if you want to discover the idea of the logarithm by starting out with exponential functions, you're in the right place, so let's get to it. Okay, so I have a very simple exponential function written up above, so it's just y is equal to 3 to the power of x. So just as a kind of a starting point, let's say we know some stuff about this. So if we just made a little table of values for x and then 3 to the x. If I put in -2, -1, 0, 1, 2, those are kind of my go-tos if I don't have a really good reason to use other values, because they tend to keep things nice and small, especially if you have functions that their kind of nice points are centered near the y-axis. So in this case, we're going to get 1/9, 1/3, 1, 3, and 9. So those points would lead to a little picture that looks something like this. I'm just going to sketch it with no actual labeling here. So it's going to look something like that. Normal, typical base exponential function. There it is. So what would the inverse of this look like? Well, if you followed along with my video from a while ago about inverses, you'll know that one of the simplest ways to look at the inverse is basically just knowing that if you have a function that takes x's and turns them into y's, then if there is a relation, or maybe a function, that takes those y's and turns them back into x's, that's what we want to do here. So we want a 1/9 to turn back into a -2. We want a 1/3 turn back into a -1. We want a 1 to turn back into a 0, a 3 back into a 1, and a 9 back into a 2. So how are we going to do that? Well, those starting values are now your inputs. So those are your x values. The y values are the old x values. So you're going to get something that looks like this. Now, I didn't do a good job. That's not true at all. Like this. And we would have, if there was a y equals x dotted line, it would look something like that. And so we would get something that's a reflection across that y is equal to x line. Now, probably if I had made some actual points, I wouldn't have made the mistake of giving it a horizontal asymptote when it definitely shouldn't have there. At least I caught it pretty early on. All right, so the idea is we're going to get something that kind of looks similar. The funny thing is that it's going to grow so fast for this function. This one is going to basically slow down to a crawl at the same sort of rate. So if you have gotten into this concept, which I try to push, that exponential functions grow exceedingly large so fast, they're very interesting, then this new thing, whatever it is going to be the worst growing function ever. It's going to be so slow in comparison. To kind of give you an idea, when we're out at 9, it's only a 2, but it would take till 27 to get to a 3 and 81 to get to a 4. So y value of 4 only occurring at 81, even though at the beginning it just kind of shows promise. It jumps up to, or it starts at a 1, or starts at, when you put in a 1, it gives you a 0, but then it goes up to a value of 1 only by going 2 units further to a 3. So it seems like it's going to have some reasonable growth, but it definitely just dies completely in the not too distant future. So this is kind of the concept of what the inverse of an exponential function is. Now, we can say pretty clearly that the exponential function to begin with, it passes horizontal line test at all y values, which means that the inverse is not just an inverse relation, it's a function. And that inverse function is going to look like this algebraically. We can just take the original statement, which is y is equal to 3 to the x, switch the x's and the y's, and get x is equal to 3 to the y. So there you have it. That is the inverse function for an exponential. Except for we really have a thing where we like to be able to solve our functions for the image or the range values, I guess, the y values. This is not solved for the y values. The y value is stuck up in the exponent of the exponential function, which is not good for those of us that don't really know what logarithms are or have seen them before, because we just don't have a way to sort ourselves through that. So what we're going to do is we're just going to say that's fine, but we're going to give it a new notation. So this is equivalent, 100% equivalent, to if we were to say y is equal to log base 3 of x. So we are going to say that those are the same statement, and we're going to call then this inverse function the logarithm. Now, generally, logarithms will look like this, although not all logarithms will look like that, and we'll get into some of the rules for that maybe in my next video. I'll kind of talk a little bit more about base transformation, or the base logarithm function and transformations of it. Maybe we'll talk a bit about the features that are there graphically. But just for the time being, I just wanted to develop the idea that there is an inverse, that it would have this look to it, and we can give it a new notation that looks like this. So this is logarithmic notation. You'll see it a lot probably, especially if you're solving exponential functions or dealing with logarithmic functions. They kind of weave in and out, just like it's really hard to talk about multiplying without dividing in an algebraic sense, or addition without subtraction, etc. So these are inverse operations, if you think about it as being an operation, or inverse functions, if we're looking at it that way. So the only other thing I want to note is that there are actually two special flavors of logarithms. So because they come up relatively often, there is the inverse to y is equal to 10 to the x, which of course is just x is equal to 10 to the y. It has notation that looks like this. Just y is equal to log x. Now, the weird thing about that is it's one of those things where it's an unwritten number and it becomes a particular value. Unwritten numbers when multiplying are 1s. Unwritten numbers on radical symbols are 2s. Unwritten numbers on logarithms are 10s. So if you don't see a base written down, that is generally referred to as the common logarithm. So I'll just call it common log. And it's a log base 10. That isn't entirely true across the board. I've seen some places that I would say are not disreputable that use the common log notation that I've written down right now for something else known as the natural log. I don't like it that way. I like it as the common log. Most calculators I've used also see it this way, so I would say that it is the most common notation for the common logarithm. The other one is actually somewhat unexpected at this point, because you may not know or have much of a feel for why e as a constant is an important number. So I'm just going to drop the notation to start things off, and we'll get to what's going to be useful about it later on. So y is equal to e to the power of x. So e is a number that is irrational, kind of like pi, and it's actually not super far off of pi, 2.718-ish, I believe. And so it, again, just kind of keeps going with no particular terminating value for those decimal places. And it has some really cool properties, especially when looked at in this setting for the exponential function. It comes up so often because of those neat properties that it gets the second of the unique notation conventions for the logarithm. We would again be able to say that in this case x is equal to e to the power of y, which we're going to say is equivalent to writing y is equal to ln x. And we call this one the natural log. Now, the natural logarithm, the way that we usually say that one out loud is ln. Like if I were to go out and mow my lawn to cut the grass, I would say y is equal to ln x if I were trying to describe this out loud to somebody. So this is the other unique one. Obviously, it doesn't have the same problem where you have to say, well, what does the unwritten number mean in this case? It just has totally different notation. It gets its own ln on the front that's totally unique to it. Now, it is the same thing as y is equal to log base e of x. You'll very rarely see that written down, but it does mean the same thing. So that's my introduction to the inverse of the exponential function. So we've seen that it has a nice graph that would be a function. But not only that, we can just do the quick switcheroo of our x and y values algebraically and see that there's not a whole lot we can do with it. So if we want it to be solved for y, it gets its own notation. That does mean the same thing as the y value stuck up into the exponent position. But it doesn't look that way, and we like it when it doesn't look that way. So new notation for us, and being able to move back and forth between the two notations is a pretty good skill. So you want to practice that sort of thing early on as you're getting used to it. Hopefully that was helpful. If it was, like, subscribe, and as always, take care, folks.